Okay, our third free response from this section, 2015 practice stuff. We've got a table of information, so we've seen these before, and we're often asked to estimate a slope at some point in here. We could be asked to use a Riemann sum to get some area. So you should, if you see one of these, I would want you to be very confident. Particularly the y values are a rate, feet per second. So integrating a rate function or finding a slope at a certain point is fair game. So Kathleen is skating on a straight track. She starts from rest at the starting line at t equals 0. That's going to be like our initial value if we need that later. Times are 0 to 12, inclusive of 12. Her velocity is measured in feet per second. It's differentiable and increasing. The fact that it's increasing, they rarely say that unless you wind up needing it at some point. Differentiable means it's going to be okay to try to estimate a slope anywhere. And values of k are given at various times above. So the first part A, use the data in the table to estimate her acceleration at time t equals 4. Now, they tell you k is her velocity. So to get acceleration, we just have to find the slope of velocity at time t equals 4. Well, as we've seen many times before, when they ask you to estimate at t equals 4, notice that is smack dab in the middle between the two data points that we have at 3 and 5. So all you have to do is say that the acceleration at 4 is approximately going to be the difference in the y's, 10 minus 5, over the difference in the x's, 5 minus 3. And of course we get 5 over 2. It says show the computation that lead to your answer and include your units. Real easy. Your numerator is feet per second, and your denominator is seconds. 5 seconds minus 3 seconds, so we can just write that as 5 feet per second squared. You should hope for one that's that straightforward. Okay, again, part B, here we go. Use a right Riemann sum with 4 subintervals indicated by the data, so that means we should be able to get an interval here, 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 and here, or between these two, between these two, between these two, and between these two. I took the liberty of drawing a quick little sketch of the graph. It only took me about a minute, maybe not even that. I think it makes these problems like ridiculously easy if you do picture. You just can't screw up this way. But if you don't want to waste the time in the minute, you can certainly do this as long as you understand what's being asked. So we're going to be asked for the area under this unseen curve between 0 and 12. Because it's a right Riemann sum, that means we're going to make our rectangles using the height at the right edge of the rectangle. That's all right Riemann sum means. So if we think about the rectangle formed in between 8 and 12 here, we're just going to use the height here and come straight across. So we come straight across and we come down. Very easy to find the area of that. The width is 4, and that's being multiplied by the height at that point, which is 24. So when they say, actually they didn't even say show your computations in this one, so we can just kind of do what we need to do. But 24 times 4 is 96. For the next interval between 5 and 8, we're going to use the height here and come across and come down. So we're going to do that, come across and come down. The width there is 3. The height is 20. So 20 times 3 is 60. And again, proceeding, we've got a height of 10 and a width of 2. 10 times 2 is 20. And lastly, we've got a height of 5 and a width of 3. 5 times 3 is 15. So all we have to do is 15 plus 20 plus 60 plus 96. Now there's no calculator allowed here. So yes, we're going to have to do that arithmetic by hand. Let's see, that's 80, and 96 is 176, plus the 15 is 191. So there's your total area, which would be the units of measure, because we were integrating, feet per second times seconds. Feet per second multiplied by seconds is going to give you feet. So this is the net, I'm just going to rewrite it, 191 feet. And That's the, because it's all positive, it's the distance traveled from 0 to 12. If the y values went negative, it wouldn't be the distance traveled, it would be the net displacement. Anyway, it says, is this approximation an overestimate or underestimate? You can imagine the curve connecting these guys, whatever it might look like. It said it's an increasing function, and because it's an increasing function, the y values on the right side of every interval will be higher than the y values on the left side. So as we come across, we're always going to be gathering up some extra area that was not underneath the curve. So we could just say this is an overestimate as k is an increasing function. That's enough. That's all I have to say. Continuing on now to part C, they now introduce Nathan into the story, who's starting 5 feet ahead of Kathleen at time equals 0. So there's a very important initial condition. Now, if you go back to the original question, it tells you that Kathleen starts at the starting line at time t equals 0. So basically, his position is 5 feet in front of the starting line. So you've got a situation like starting line there. Kathleen does her thing. Nathan starts here at position equal to 5. So they're probably going to say, where is he after a certain amount of time? And now we read the question. It's his velocity is given, and it says, write but do not evaluate an expression involving an integral that gives Nathan's distance from the starting line at time equal to 12. So basically, we have the situation that he starts here at 5, and then for 12 seconds he's going to go. And if we can just find the net change in his position from time 0 to time 12, that's going to give us how far this red line is, this red squiggly. And so all we have to do is add 5 to that, and that'll be how far he is from the starting line. So let's do that. Let's have his position will be 5, which is where he's starting, plus the integral of his velocity from 0 to 12, and that velocity is 150 over t plus 3. There we go, minus 50 e to the negative t. Maybe put brackets around that whole thing with a dt. And it's just write but do not evaluate. And there's the integral, and that's going to tell us this far. And we're going to add 5 to that, which is going to tell us what his position is. So there you go with part C. That was easy enough. On to part D, write an expression for Nathan's acceleration. We've been given his velocity, this function right here. So n of t is his velocity, which is 150. Acceleration, of course, is the derivative of that. So we're going to do the quotient rule on this first term here, and then we're going to do basically a chain rule here. Quotient rule, low d high, low is t plus 3, but d high is 0. The derivative of 150 is 0. So we can just leave that part off. Minus high, which is 150, d low. The derivative of the denominator is 1. Draw the line down below. We get t plus 3, the denominator squared. Now we have the derivative of negative 50e to the negative t. So I'm going to write negative. The derivative of 50e to the negative t is 50e to the negative t multiplied by the derivative of this exponent with respect to t. And the derivative of that, of course, is negative 1. So this gets multiplied by negative 1. So cleaning this up, n prime of t is negative 150 over t plus 3 squared plus 50e to the negative t, because a negative times a negative is a positive. We can put a box around that, and there is his acceleration. All done. That's a pretty straightforward problem. I would expect my students to get at least 7 out of 9, maybe all 9 out of 9 on that one.